In this session, we'll explore two activation functions for artificial neural networks. Let's recall from the previous class that the summation is we had u, and we can represent that as a function that has a vector argument where it's implicit that we have data in it. And we could write that as we could take the transpose of the data that the user gives us and append a 1 to it, multiply that by our augmented weight vector, and what we'll prefer to do is write that as a 1 form times a weight vector. And an artificial neuron uses an activation function. And we will write this activation function using the Greek letter phi, and this will take a real number in, such as this value u, and it will produce a real number. So it's a function that has a scalar argument, and this is how we'll do it. Some others will write this as a function that has a vector argument. So when you go to read other material, please be sure that you understand what the assumptions are and what is being mapped. So we need to ensure that this function and the labels are compatible. And this compatibility is simply that, for example, in artificial neural networks, the convention is that y is binary, 0 or 1, and we then try to have this function bounded between 0 and 1. If the labels were -1 and +1, then we would have different bounds for that. So that's what we mean by compatibility. And we will write the derivative as, the derivative of the scalar, and we'll write that as the Greek letter psi. And this is just a shorthand. This usually, the activation functions we'll look at usually have such straightforward derivatives that we could just write the prime. We'll add this psi in because later on it might help us in formulations. So the usual one is the sigmoid, and it's also called the logistic function. And it's called a sigmoid because its graph has an S-curve. That is, the graph looks like, if this is our parameter u and this is the activation function, it looks like this. That is, it's got an approximate S shape. And this is an example of what I mean by compatible. The kind of activation function we're going to look at in this session is one that's bounded between 0 and 1. So what we'll do is we'll sometimes write this as the score, sigmoid, and we'll write the activation function, and then when it matters, we'll put an S for sigmoid, and that has a scalar argument. And this, the one we'll use, we can write this concisely as 1 over 1 plus e to the minus u. And this, from previous from prerequisite material, is the logistic function, and it's closely related to the odds of some data being on the positive side of a hyperplane. The derivative of the sigmoid, which we'll write as the Greek letter psi, and we'll subscript that with an S to indicate is the sigmoid. After we do our differentiation and then rearrangement, we can write this as the sigmoid of u times 1 minus the sigmoid of u. And it's probably a good idea for you to take out some pen and paper and do the differentiation and do the algebra to convince yourself that this formula is correct. Another activation function that's often used in artificial networks is it's sometimes called the Relu. And this is the rectified linear unit. And this, the scoring function, when we use it, we'll subscript that as an R for Relu, and that is our activation function Relu, and that is the maximum value of 0 and u. Let's graph this to see what it looks like. So here we have our scalar value u, and here we have phi. Oh, we should probably have put a little s there. Here we have phi r that has this argument, and what this looks like is that if u is less than 0, then the maximum of 0 and a negative number is 0, and so this will have a 0 value. And then if u is strictly greater than 0, that is, if u is positive, the max function will simply return u. And so this will go on upwards to infinity. And this activation function is really fast to compute. You can do it with a max, or you can do it with an if statement, and that means that it's very, very quick to compute, whereas with this, you have to compute an exponential, and that's usually done by an approximation with a Taylor series, which requires substantially more computation on most machines. And this empirically gives very good performance. Now, what's the derivative of that? Well, that would be, we could write that as the derivative of the Relu, and that is, we'll also write that as the psi function for the Relu, and that is, now we can look at this graphically. That is 0, that is, it's perfectly flat if it's less than 0, and it's 1, the derivative of u with respect to u is 1, and so we can write that derivative as that is the Heaviside function of the scalar variable. And these two are very fast to compute, and although they are not ideal for the output layer, when you have a multi-layer neural network, it's quite common to have the internal or hidden layers using this Relu computation because it's fast and empirically it's pretty good.